Alright, let's look at the competition between substitution and elimination reactions. When you're comparing SN1 and E1 reactions, it's kind of a toss-up. But it's easier to control which will win, elimination or substitution, when the mechanism goes by the SN2 or E2 mechanism. So let's look at what affects the likelihood of an SN2 versus E2 mechanism. The first factor is the strength of the nucleophile. If it's a really strong base, it's going to be more likely that an elimination reaction will occur. The way I think about this is I ask myself, what does a base do? Well, it accepts a proton. So here's hydroxide here accepting a proton, and the hydrogen gets kicked off, and we have a good old E2 elimination reaction. Another factor that affects whether SN2 or E2 wins is the classification of the carbon that has the leaving group. We're talking about this carbon here. If it is a tertiary carbon bonded to 3 other carbons, it favors an elimination mechanism. And now, my reason for this may or may not be entirely true, or may just be a very small, it may only a little bit contribute to the explanation for that, but here's the way I think of it. A tertiary carbon is going to have all sorts of crap surrounding it, so it's going to be sterically hindered. Therefore, for an SN2 reaction to happen, our base would have to try to get through all that steric hindrance and get in to react with that tertiary carbon, and that's harder than the base just moseying up out here, encountering no resistance, and grabbing a hydrogen from another carbon. And if it was just able to sidle up and without any steric hindrance just grab the hydrogen from this carbon over here, that's going to allow the elimination to happen. That explanation definitely is true and definitely applies when you think about the size of the base. If you have a really big base, here's a classic example of a sterically hindered base, tert-butoxide. It's gigantic, look at it. It's gonna be impossible for that to make its way into try to do an SN2 reaction with the middle carbon. That's not going to happen. But it can get close enough to this molecule to grab one of the outer hydrogens over here and cause an E2 reaction to happen. So the bigger the nucleophile, the more likely it is that the E2 reaction mechanism is going to win. Here's a curious thing about E2 reactions. Let's look at the conformations of the reacting molecule here. It could either be anti or syn, where the leaving hydrogen is across from the leaving group, or where the leaving hydrogen is on the same side as the leaving group. Let's look at the interactions going on when elimination tries to happen when the molecule's in the syn position. The base comes in, and the base is usually going to have a negative charge. The base is going to have to get, when it takes off the hydrogen, it's going to have to get pretty close to the leaving group. And the leaving group, as the base comes in, becomes more and more negatively charged. So this interaction between the two negative charges here is unfavorable. And the result is that the anti-conformation is the conformation that E2 reactions happen from. So you don't really see E2 reactions happening from the syn conformation. The other reason has to do with orbital overlap. So let's not go too much into that. Let's look at a effect of this necessity to have the molecule in an anti-conformation. We know that the E product is going to be more favored over the Z product because the Z product has more of a interference. There's a clash between these two bigger groups on the same side. So if the molecule, when it undergoes an E2 reaction, can make an E product, it will. And it can always make an E product in an E1 reaction mechanism, because that one goes through a carbocation intermediate. But we are currently looking at E2 reaction mechanisms, where the molecule that reacts has to be in an anti-conformation. I've drawn this one over here such that when the hydrogen and the leaving group are in anti-conformation, the other groups are in the positions that will make them form a Z product. So here both the methyl and the ethyl group are pointing away from us, so they're going to end up on the same side. You're going to get a Z product. And it's not going to be as stable as the E products would have been, but we're going to have to settle for Z. If the molecule could have reacted from the syn conformation, look, then it could have made the E product, because the methyl group over here would have been coming toward us, the ethyl group over here would have been going away from us, the bigger groups would have been on opposite sides, everybody would have been happy. If, however, well, this problem can be avoided if there are two hydrogens on the carbon that loses a hydrogen. So if this were a hydrogen here, then this guy would rotate 120 degrees like that. Then it would get in a conformation like this, and the big group here would be opposite to the big group over here, and you get an E product. And this part of the molecule will just rotate until the right hydrogen was anti to the leaving group in order to form the E product. Here's another effect of this necessity for having an anti-conformation. In a ring, here's a cyclohexyl ring with a chlorine on it. The chlorine and the hydrogens can only be anti if they are in axial positions. So the ring has to be in a conformation where the chlorine's in an axial position, and then it can only, these two hydrogens that are also axial can come off with the chlorine, but not the equatorial one here, or the equatorial one here. So what if instead of a hydrogen down there, there was some kind of alkyl group in this molecule, and it was in a trans position, such that when the chlorine was axial, the alkyl group was always axial. This would slow down the rate of the reaction because now there's only one hydrogen that can come off. But no, let's look at a third molecule here. Maybe this molecule has two alkyl groups that are trans to the chlorine, and when the chlorine's axial, they both have to be axial. Let's see. This is not going to favor an E2 reaction because now there's zero hydrogens that can be anti to the chlorine. And anyway, the molecule doesn't want to be in this conformation with all these big axial groups. It would rather have them be equatorial. So if these alkyl groups were equatorial, maybe it would actually help out the rate of an E2 reaction. Let's put them equatorial. Now the alkyl groups are in a cis position relative to the chlorine, and when the chlorine is axial, they're both equatorial. So the molecule actually wants them to be equatorial, so this is a pretty stable conformation for this molecule. And now, again, there are two hydrogens anti to the chlorine. So here's your elimination. It can happen now. Anti. The end.